This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2019 AP Calculus exam, free response question AB6, namely the squeeze theorem. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. First, I'll state a preliminary property of limits related to the squeeze theorem, and then I'll state the squeeze theorem. And I'll illustrate this result graphically. And then I'll show a detailed application and use technology to illustrate this result. And finally, I'll leave you with several examples that involve the squeeze theorem. I really think of these two theorems on this page as properties of limits. And I think both of these theorems are reasonable and intuitive. And they're useful additional properties for finding certain limits. The first one says that if f is always less than or equal to g near a, or in a neighborhood of a, then the limit of f must be less than or equal to the limit of g. Here's the formal statement. If f of x is less than or equal to g of x for all x near a except possibly at a, and the limits of f and g both exist as x approaches a, then the limit as x goes to a of f of x is less than or equal to the limit as x goes to a of g of x. And here's the squeeze theorem, which is useful in a variety of limit contexts. If f of x is less than or equal to g of x is less than or equal to h of x for all x near a except possibly at a, and the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x is equal to L, so the two outside functions are zeroing in on L, then the limit as x goes to a of g of x is also L, so the sandwiched function or the squeezed function must also be zeroing in on L. The squeeze theorem is also sometimes called the sandwich theorem or the pinching theorem. And here's an illustration of that theorem. It says that if g of x is squeezed between f of x and h of x near a, and if f and h have the same limit L at a, then g is squeezed or forced to the same limit L at a. Here's a classic example that illustrates the use of the squeeze theorem. Let's show that the limit as x goes to 0 of x squared times the sine of 1 over x is equal to 0. Now this takes a little bit of problem-solving skill to realize that we can solve this problem using the squeeze theorem. The first thing we often try in order to solve a limit problem is direct substitution. But that doesn't work here, because the sine of 1 over x is undefined at x equals 0. Now the next thing you might consider is that limit property that says the limit of a product is the product of the limits. But this is only true if both limits exist. And the limit as x goes to 0 of the sine of 1 over x doesn't exist. Do you remember why? It's because sine of 1 over x oscillates between -1 and +1 infinitely often, and it never zeroes in on any one value. So we need another method to find this limit. And if we're going to use the squeeze theorem, then we need to find a function f that is less than or equal to g near 0, and a function h that is greater than or equal to g near 0. We can find these functions f and h by using the properties of the sine function. We know that the sine of any number is between -1 and +1. Now, multiply all parts of this inequality by x squared, which is a positive number. So the direction of the inequality doesn't change. Now, I have the original function bounded near 0. And I can find the two outer limits easily by direct substitution. Therefore, by the squeeze theorem, the limit as x goes to 0 of x squared sine of 1 over x is equal to 0. Here is some confirmation of this result using technology. Here's a graph of x squared minus x squared and x squared times the sine of 1 over x, near 0. You can see the oscillations in the x squared sine of 1 over x and how this function is bounded by the other two functions. And using the TI-Nspire, I can actually evaluate this limit directly on a calculator page. And you might also consider a table of values to demonstrate how the squeeze theorem works numerically. Here are a few applications for you to try. In Part A, use the squeeze theorem to show that the limit as x goes to 0 of g of x is also equal to 0. And illustrate this result using technology. In Part B, use the given inequality to find a limit as x goes to 3 of f of x. And in Part C, it seems reasonable that the squeeze theorem also works with one-sided limits. So, try to find this limit. I hope this video provides some insight into the squeeze theorem and how to illustrate this result graphically, and provides a few AP Calculus type problems. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.